Hey guys, this is Angel, and today we're going to be talking about work in physics. Now, work is generally something, I think it's safe to say, something that people don't enjoy doing. And why is that? It's because work requires us to force ourselves and move ourselves to expand energy, which is the measurement for work in physics. And the unit for work in physics, unit for energy, is joules. But let's take a look at the definition of work here, which work is done when a force that is applied to an object moves that object. So we need to have the movement of an object and force being applied to that object. And we can see that how the definition for work is related to the equation for work. We got force and distance, or delta x, displacement, being proportional to work, or being in the equation for work. We also have this cosine theta here, which I'm going to explain a little later in the examples that we have. But in brief, it's that cosine theta is important when you have a push or pull at an angle, because that angle to push or pull has a horizontal and vertical component. And generally we want to look at the horizontal component if we're moving a box on a flat surface, let's say. So another thing we're going to be discussing here is the work energy theorem. So the work energy theorem is the idea that the work done on an object by the net force is equal to the change in its kinetic energy. So I want to go back to this equation real quick. We've got work is equal to force and delta x. So we talked about how if you've got work, you've got force. Now, in earlier videos and earlier in the course, we discussed how if you've got force, if you have a net force, I should say, if you have a net force and a net work, then you have an acceleration. If you have an acceleration, then you have velocity. So that acceleration is giving you a change in the magnitude of velocity, or the speed of an object. And whenever you have a change in velocity, you have a change in kinetic energy. If you have an acceleration, it might mean that you are looking at a change in direction, like we do when we discuss centripetal force, but we're not quite there yet. So again, the work energy theorem is the idea that the work done in an object by the net force is equal to the change in kinetic energy. And that's because if you have a net force, you have acceleration. And if you have an acceleration, you have a change in velocity or speed, meaning that you have a change in kinetic energy. So that is how that work energy theorem plays out. And I'm hoping that we can go over some examples here together that will further discuss not just work, but also the work energy theorem. And so in this first example, we have a 13 kilogram box that is lifted 12 meters vertically. And we were trying to find out what is the work that is done by gravity on the box. So that might sound kind of odd to you. What is the work done by gravity? The reason that sounds odd is because we don't necessarily think of gravity as an entity. It's not a person or a rope or anything that's physically pushing on something, but this is what we call field forces. In short, it's important to remember that a force is anything that gives a push or pulls. And so a gravitational force is a pull from the gravitational field of the Earth. And so that's why we would consider that pull force in our work equation. And so let's take a look. Let's go ahead and solve for what that work is being done on this 13 kilogram box. So work is equal to force cosine theta delta x, or displacement. And again, it's always a really good thing to memorize these equations and understand why they are written certain ways. Why is it that work is proportional to force and to delta x? And so in this case, what is the force that is acting? Well, that's the force of gravity. So force of gravity is equal to the mass times gravitational acceleration, which is 10 meters per second squared. And so work is equal to 130 newtons, right? So we got that by doing 13 kilograms times 10 meters per second squared is 130 newtons. Now the cosine theta here is, I know I discussed how we are generally relating it to the horizontal, but in this case, with a direct lift upward, we're looking totally vertical. And since this isn't going on at an incline or any sort of angle from the vertical, then we're going to say that the cosine of theta is equal to 0, which will make it equal to 1. And then we're going to look at our displacement. Our delta x is 12 meters. It's given for us. So when we do those calculations, we get that work is equal to 1,560 joules. And so hopefully you can do that without a calculator. I always like to remind people that you don't get a calculator on the MCAT, so you definitely want to practice as much mental math as possible. You could have done that by doing 13 times 12 is 156, then just add the 0 from the 130, and then you would get 1,560 joules. So that is the work that is done by gravity on the box. And so as you're lifting the box up, you're lifting it against the force of gravity. So gravity works 1,560 joules against you to try to keep the box down. And so now let's take a look at the next question. What would be the final velocity of the box if it were directly dropped down to its original position? So this is where the work energy theorem comes in. And I think this is a pretty cool theorem. Whoever discovered this and related the equations was obviously crazy intelligent. How are we going to do this? Well, we talked about how the net work on an object is equal to its change in kinetic energy. And that change in kinetic energy equations look like this. It's 1/2 mv final squared minus 1/2 mv initial squared. Right, so we have a final velocity, an initial velocity, and so that's how we get a change in kinetic energy. That equation there is the change in kinetic energy equation, also something that you should have memorized. And then we got our net work previously, which was 1,560 joules. So what else can we look at here that we can cross out? And I'll just give you that right away, is we can take out this initial velocity, because when we're at the top, we're not moving, and it's not specifically stated in the problem, but we're going to assume that when we get to the 12 meters above the ground, we are at a velocity of 0, so we can actually just cut that out right there. And so now all we need to do is solve for the final velocity. Here is what we're looking for. And let's go ahead and practice our mental math. 1,560 times 2 would be 3,120 joules. So 3,120 joules is equal to the mass and then the final velocity squared. So 3,120 joules divided by 13. Also something we can do mental math wise. I'll show you how I do it. Is 13 goes into 31 2 times. You got 5 left over. You got 2. 13 times, let's say 4 would be 52. Okay, so 13 times 4 is 52, 0, 0. You got 240 joules is what we have left. I'm sorry, not joules. 240 meters squared over seconds squared is what we have left over when we divide by the mass. And the reason I got meters squared over seconds squared right off the top of my head is because I know that when I take the square root of both sides, I have to get meters over seconds in order to get my velocity. So I'm going to take the square root of both sides, cancel out that square on the final velocity, and we got that the square root of 240, again, mental math, even though this one is obviously a lot tougher, you can solve if this was multiple choice to give you something very reasonable. I know that the square root of 14, the square of 14 is 196, and the square of 15 is 225. Okay, so that's getting pretty close. And then the square of 16, I actually don't know that off the top of my head, but I do know that it's going to be greater than 240. So if I were doing the MCAT, I would choose the answer that was closest to 15.5, let's say. And I think that when you do that calculation, the square root of 240, you do get something pretty close to 15.5. And so let's recap real quick. We were able to get the work of the work done on the box by using our work equation, and for the cosine of theta we put in 0 because we're looking at the vertical plane instead of the horizontal plane. And that work, that net work, that is now gravitational potential energy, which is what we'll discuss in the next video. That gravitational potential energy was converted into kinetic energy, right? So that net work of 1,560 joules was converted all to kinetic energy when the box was dropped. And that's what we call the work energy theorem.